Back in 1935, something really weird happened. Albert Einstein, the guy who literally wrote the rulebook for the cosmic speed limit, stumbled upon something that seemed to shatter his own rules. He was pretty sure it was just a bug, a flaw in this wild new theory called quantum mechanics. But, as it turns out, the universe is way, way stranger than even he could have imagined.
We all hear it, right? Nothing travels faster than light. But have you ever stopped to think why that's such a big deal? See, the speed of light isn't just fast. It's the universal glue holding cause and effect together. So what would happen if something actually broke that speed limit? It's a question that genuinely kept Einstein up at night.
So yeah, this whole idea of a cosmic speed limit, that comes straight from Einstein's theory of relativity. And it's not just some friendly suggestion, like a speed limit on the highway. Nope, it's a fundamental pillar of physics, the one thing that protects the very fabric of reality, making sure that causes always happen before effects. Okay, so why is this rule so important, so unbreakable? Well, to get that, we actually have to go way back to a huge problem that even the great Isaac Newton was stumped by.
So in Newton's world, picture this: if the sun just, poof, vanished, Earth would instantly, in that exact same moment, fly off into space. Einstein looked at this idea of action at a distance and thought, no way, that's just absurd. I mean, it could lead to all sorts of paradoxes where you'd see an effect happen before its cause. So his solution was brilliant. He said gravity isn't instant. Its influence has to travel, rippling through space-time, and it can't go any faster than the speed of light.
And that right there gives us this absolutely crucial principle called locality. What it means is, an event right here can only affect its immediate surroundings. And that influence, it spreads out, but never, ever faster than light. This is what keeps cause and effect in the right order for everyone, everywhere. It was a beautiful solution. Problem solved, right? Well, or so he thought. So after putting together this beautiful, orderly, local universe where everything makes sense, Einstein turned his attention to this messy, weird new theory on the block, quantum mechanics. And what he found there, well, it threatened to shatter his whole perfect picture.
You can just imagine the scene. It's the legendary 1927 Solvay Conference. Einstein gets up in front of all the founders of quantum theory and basically tells them their new rules demand some kind of peculiar mechanism of action at a distance. What he was really saying was, your theory directly contradicts my own principle of locality, the bedrock of relativity. And the source of all this drama? It's a phenomenon we now call quantum entanglement. Einstein had a much more famous name for it, though. He called it spooky action at a distance. And it really is spooky. It's this mysterious, invisible link between two particles that connects their fates instantly, no matter how much distance is between them.
Okay, so this all leads to the famous EPR thought experiment. Let's break it down. Imagine you have two of these entangled particles. They have a property called spin. You can just think of it like a tiny compass needle that's either pointing up or down. Now you set them up so they have opposite spins, and you send them flying apart, like way apart. The second you measure one particle and see its spin is up, you know, at that very instant, that its partner, even if it's clear across the galaxy, has to be down.
And that is the billion-dollar question, isn't it? How in the world did that second particle know the result instantly? Did some kind of information just travel faster than light, completely shattering the cosmic speed limit? Well, this kicked off one of the biggest debates in the history of physics. On one side, you had Niels Bohr, the champion of quantum mechanics. He was adamant that this spooky connection was just real. That's how the universe works. But Einstein, he just couldn't accept it. He argued there was no spooky action at all. Instead, he figured the particles must have carried some kind of hidden instructions from the very beginning, a pre-written script telling them what to do.
So for decades, that's where it stood. It was just a philosophical argument, really. You could believe in Bohr's spooky story, or you could side with Einstein's more sensible, local story. But then, this physicist named John Bell came along and realized, wait a minute, we can actually test this. It's kind of wild, actually. After Einstein and Bohr both passed away, the whole debate just fizzled out. It was mostly forgotten. But then, in 1963, John Bell just happens to stumble across Einstein's old paper, and reading it, he has this absolutely brilliant realization. Bell's genius was in coming up with this incredibly clever twist on the whole experiment. He figured out a specific way to do the measurements where Einstein's hidden instruction story and Bohr's spooky connection story had to predict different results.
It was basically a way to put nature on the spot and forced it to show its hand.
So here's what he predicted. It's all about something called the disagreement rate. If Einstein was right, if there were local hidden instructions, the results would disagree at least a third of the time. That's 33%. But if Bohr was right and the spooky quantum connection was real, they'd only disagree 25% of the time. All of a sudden, this decades-long debate wasn't about philosophy anymore. It was about a number. All anyone had to do was run the experiment and see what they got.
And the result? Well, every single time the experiment has been run, from the very first groundbreaking tests all the way up to the super advanced setups we have today, the answer has always been the same. Einstein was wrong. The disagreement rate is 25%. Spooky action is real.
So, what on earth does this all mean? It means we have no choice but to face a reality that is far, far weirder than even Albert Einstein was comfortable with.
You know, John Bell himself said it best. The results of these experiments, they force us to accept that the universe is non-local. That's a huge deal. It means there really are influences that connect things faster than light can travel.
Okay, so this is obviously the big question, right? If these faster-than-light influences are real, does that mean we can build some kind of faster-than-light telephone? Could we send messages back in time and completely break causality?
And here is the absolutely crucial twist, the thing that saves reality as we know it. While the influence is instantaneous, the outcome of any single measurement is completely, totally random. You can't force a particle to be up or down whenever you want, and because of that, you can't actually use it to send a message. So spooky influence, yes. Spooky information, no. Causality is safe.
But is there any way out of this? Is there some kind of loophole that lets us have our nice, local universe without all this spooky action? Well, there is one alternative. And honestly, it might be the strangest idea of them all.
It's called the many worlds interpretation. And the idea is this. When you measure that particle, the universe itself splits in two. In one reality, you get the up result, and in a completely new, parallel reality that just branched off, you get down. Both outcomes actually happen. So in this view, you don't need a faster-than-light signal because nothing was ever decided in the first place. The universe just branched. And that leaves us with this incredible, mind-bending choice. Do we live in a single universe that's non-local, all connected by these faster-than-light spooky influences, or do we live in a local multiverse that is constantly branching into an infinite number of parallel worlds with infinite versions of you? So far, physics just can't tell us which one is true.
So what is it? A single, strangely connected universe? Or an infinity of branching worlds? Whichever path you think is right, one thing is for sure. Reality is so much stranger than it seems.